Across one of the most remote frontiers on Earth, where endless fields of white stretch beyond every horizon and temperatures remain hostile to almost every form of life, an enormous river of ice has quietly entered a period unlike any witnessed during modern science. For decades, it appeared almost timeless, advancing so slowly that a human lifetime seemed insignificant by comparison. Yet satellites orbiting hundreds of miles above the frozen continent have revealed a different reality. Aircraft carrying sophisticated radar have peered through nearly 1 kilometer, about 6/10 of a mile, of solid ice. Autonomous underwater vehicles have ventured into hidden cavities where no sunlight has ever reached. Together, these efforts have uncovered mounting evidence that one of Antarctica's largest glaciers is steadily losing the natural defenses that have restrained it for centuries. The glacier is known as Thwaites, although its more dramatic nickname, the Doomsday Glacier, has become far more familiar to the public. The label captures attention, but it also carries the risk of misunderstanding. Images of towering ice cliffs crashing into the ocean and headlines predicting an imminent global catastrophe often leave the impression that the glacier is on the verge of vanishing overnight. That is not what the science says. Instead, researchers describe something both less immediate and, in many ways, more profound. A process already underway, unfolding over decades and centuries, with consequences that will shape coastlines long after today's generation has passed. Fresh findings published throughout 2026 have sharpened that picture with remarkable clarity. Rather than revealing signs of recovery, independent teams studying the glacier from space, from the air, across the ocean, and beneath the ice have reached strikingly similar conclusions. Thwaites continues to thin. Its grounding line continues to retreat. Ice continues to flow toward the sea at increasing speeds. Most significantly, the floating eastern ice shelf that still acts as an important stabilizing barrier is showing increasing signs of structural weakness. Scientists warn that this remaining support may not endure much longer. Understanding why this matters requires looking beyond the glacier's spectacular size. Thwaites occupies an unusually important position within the West Antarctic ice sheet. Spanning an area of roughly 120,000 square kilometers, more than 46,000 square miles, it serves as one of the principal gateways through which vast quantities of inland ice reach the ocean. Much like a massive cork restraining water inside an enormous reservoir, the glacier slows the movement of ice from deep within Antarctica. Remove or weaken that restraint, and the entire system begins adjusting in ways that extend far beyond the glacier itself. Its nickname did not emerge simply because of its dimensions. Scientists adopted increasingly urgent language over the past several decades after recognizing that the glacier rests upon bedrock lying hundreds of meters below sea level. In many places, that bedrock slopes downward farther inland rather than upward. Such geometry creates conditions favorable for what glaciologists call marine ice sheet instability, a process capable of sustaining retreat even after the original trigger has begun. Once the point where the glacier lifts from the bed and begins floating retreats into deeper terrain, increasingly thicker ice becomes exposed to the ocean. Thicker ice floats more readily, allowing retreat to continue under the right conditions without requiring dramatically stronger warming. That realization transformed Thwaites from another Antarctic glacier into one of the world's most closely watched natural systems. International collaborations involving hundreds of scientists from numerous countries launched some of the most ambitious polar research campaigns ever attempted. Specialized ice-breaking ships navigated dangerous seas choked with sea ice. Aircraft carrying ice-penetrating radar mapped hidden landscapes beneath the frozen surface. Satellites measured tiny changes in elevation with astonishing precision, while robotic submarines slipped beneath floating ice shelves to observe places inaccessible to human divers. Each expedition answered long-standing questions while exposing new mysteries. The glacier proved far more complex than earlier models suggested. Instead of behaving like a single solid block, it responded to countless interacting forces involving the atmosphere, the surrounding ocean, the shape of the bedrock, the chemistry of seawater, and even the sediments buried beneath kilometers of ice. One of the most influential discoveries involved warm ocean water arriving from the surrounding seas. Far below the frigid Antarctic surface circulates a relatively warm water mass known as circumpolar deep water. Although only a few degrees above the freezing point, it carries enough heat to melt ice efficiently when it reaches vulnerable sections of floating glaciers. Scientists discovered that this water does not simply remain offshore. Ocean currents guide it into cavities beneath floating ice shelves, where it attacks the glacier from below. Unlike melting visible on the surface during summer months, basal melting remains hidden from view. Ice that appears solid from above may be thinning steadily underneath as warmer seawater carves channels and enlarges cavities over many years. The consequences unfold quietly. Floating ice shelves act much like enormous architectural buttresses supporting a cathedral wall. They do not stop the glacier entirely, but they resist its forward movement by pressing against surrounding islands, underwater ridges, and coastal features. Their presence slows the discharge of inland ice into the sea. As melting weakens those shelves, their ability to provide resistance gradually diminishes. During the past several years, researchers have paid particularly close attention to the glacier's eastern ice shelf. Compared with neighboring sections that have already fractured extensively, this remaining platform has continued supplying an important measure of restraint. Yet detailed observations reveal growing networks of crevasses, widening fractures, and structural damage that suggest its stability is increasingly uncertain. Recent scientific assessments indicate that this eastern shelf may approach a breaking point within the relatively near future. Such statements understandably generate alarming headlines, but they require careful interpretation. The anticipated breakup does not mean the entire glacier will collapse immediately. Instead, it marks the likely loss of one of the glacier's remaining natural breaks. Imagine a heavily loaded freight train descending a long mountain grade. Removing part of its braking system does not cause the train to vanish in an instant, yet its speed increases unless another force compensates. Researchers expect a comparable response from Thwaites. Once the floating shelf weakens beyond recovery or fragments into large icebergs, inland ice will likely accelerate toward the ocean more rapidly than before. The increased discharge unfolds over years, decades, and eventually centuries, rather than within days or weeks. This distinction has become one of the defining messages emerging from the latest scientific literature. Several independent studies released during 2026 reinforce the conclusion that continued retreat is highly likely, while simultaneously rejecting the notion of an immediate civilization-ending collapse. Among the most influential contributions is a study published in Geophysical Research Letters, where researchers compared modern satellite observations with advanced numerical simulations developed over many years. Earlier generations of models contained scenarios that once appeared unusually severe. Yet when scientists compared those simulations with present-day measurements, an unexpected pattern emerged. The glacier's actual behavior increasingly resembled those higher loss projections. Measurements of grounding line retreat, thinning rates, and glacier velocity all aligned closely with scenarios involving sustained and substantial ice loss extending through the coming decades. Just as importantly, researchers found no convincing evidence that Thwaites had entered a period of stabilization. The glacier's present condition appears consistent with long-term retreat, rather than a temporary fluctuation likely to reverse naturally. For scientists who have monitored Antarctica over several decades, that agreement carries exceptional weight. Models are valuable only when observations confirm their underlying physics. As satellite records lengthen and measurement techniques improve, confidence grows when independent lines of evidence point toward the same conclusion. At nearly the same time, another major study fundamentally changed understanding of the landscape hidden beneath the glacier itself. For many years, computer models necessarily simplified the bed lying below the ice because direct observations remained extremely limited. Researchers often assumed relatively smooth surfaces interrupted by only modest variations. Extensive seismic surveys have now revealed something entirely different. By transmitting sound waves through the glacier and analyzing their echoes across more than 340 kilometers, over 210 miles, of survey lines, scientists reconstructed an astonishingly diverse underground landscape. Instead of uniform bedrock, they discovered resistant rocky ridges, deeply buried sedimentary basins, ancient wetlands preserved beneath the ice, and remarkably varied geological formations. Those hidden features are far more than scientific curiosities. Hard rock ridges can temporarily slow glacier movement by increasing friction and providing additional resistance. Soft, water-rich sediments produce the opposite effect, allowing the immense weight of the glacier to slide more readily toward the coast. In effect, the glacier travels across a patchwork landscape where some sections function like rough pavement, while others resemble slippery mud. Recognizing these differences represents a major advance because future retreat depends not only upon atmospheric temperatures or ocean heat, but also upon the unseen terrain supporting the ice. Incorporating these geological complexities into next-generation computer models promises more reliable projections of future sea level rise while reducing one of the largest remaining uncertainties surrounding Antarctica's evolving ice sheet. Far from signaling the end of scientific discovery, those revelations opened another chapter that reached deep into Antarctica's distant past. Every glacier carries within it a history written not only in layers of ice, but also in the landscape hidden underneath and the sediments scattered across the surrounding seafloor. By reconstructing that history, researchers hope to answer one of the most pressing questions facing coastal communities around the world. Has Thwaites encountered similar periods of instability before, or are the changes unfolding today entirely without precedent? Evidence emerging during 2026 has brought scientists closer to that answer than ever before. Geological records preserved beneath the ocean floor reveal that Thwaites has indeed experienced dramatic retreats in the distant past. A study published in the Proceedings of the National Academy of Sciences examined sediments deposited after the last ice age and found repeated episodes during which both Thwaites and neighboring Pine Island Glacier retreated far inland. Those retreats did not unfold gradually over thousands of years. Instead, they advanced rapidly once critical thresholds had been crossed. The findings offer an important lesson. Certain glaciers possess tipping points embedded within their geometry. As long as those thresholds remain intact, the glacier can resist considerable environmental change. Once they are crossed, however, retreat may continue under its own momentum, even if external conditions remain relatively stable. This phenomenon, known as marine ice sheet instability, has long been predicted by theoretical models. The geological evidence now provides powerful confirmation that it has occurred naturally before. That does not mean history is repeating itself in exactly the same way. Modern warming, driven by human emissions, is introducing additional heat into both the atmosphere and the surrounding oceans at rates that differ from natural changes following the last ice age. Yet the ancient evidence strengthens confidence that the physical processes incorporated into today's ice sheet models are grounded in reality rather than speculation. Another major modeling effort released during 2026 reconstructed the glacier's evolution across much of the 20th century. By combining historical observations with sophisticated simulations, researchers concluded that Thwaites appears to have remained comparatively stable for thousands of years before experiencing a significant turning point around the 1940s. Their analysis suggests that an important western pinning point, a section where floating ice remained anchored against underwater topography, was likely lost during that period. The disappearance of that natural anchor may have initiated the chain of retreat still observed today. Rather than responding only to present-day warming, the glacier appears to have entered a self-reinforcing phase decades ago, one that has continued while additional ocean heat further accelerates the process. This finding helps explain why the glacier has shown little indication of returning to its previous state despite year after year of careful monitoring. Scientists emphasize that glaciers often respond slowly to changing conditions because of their immense size. Ice measured in hundreds or even thousands of meters thick cannot instantly adjust to shifts in temperature or ocean circulation. Instead, changes introduced decades earlier may continue unfolding long afterward. In that sense, today's observations reflect both the climate of recent decades and the glacier's delayed response to earlier disturbances. One of the most ambitious efforts to understand these interactions came through the International Thwaites Glacier Collaboration, an unprecedented partnership involving researchers from multiple countries, research vessels, aircraft, satellites, autonomous underwater vehicles, and field camps established under some of the harshest conditions on Earth. Over several Antarctic seasons, scientists collected enormous quantities of data describing every accessible part of the glacier system. The resulting publications, released throughout 2026, converged upon several consistent conclusions. Warm circumpolar deep water remains the dominant source of melting beneath the floating ice shelves. Grounding line retreat continues across vulnerable sectors. Internal fractures are increasing in both number and complexity. Ocean circulation beneath the glacier proves considerably more dynamic than earlier models assumed, transporting heat into hidden cavities through pathways that continue to surprise oceanographers. Perhaps equally significant is the growing appreciation that no single factor controls the glacier's future. Ocean temperatures, atmospheric conditions, bedrock geometry, sediment composition, tides, seasonal sea ice, and even subtle changes in ocean currents interact continuously. Each influences the others in ways that challenge even the most advanced computer models. Rather than reducing confidence, this expanding knowledge allows scientists to replace oversimplified assumptions with increasingly realistic representations of the Antarctic environment. Fieldwork conducted during the 2025 through 2026 Antarctic season demonstrated both the extraordinary challenges and remarkable achievements associated with studying one of Earth's least accessible regions. Researchers successfully drilled through approximately 1 kilometer, about 3,300 feet, of solid ice to reach the ocean hidden below the glacier. Reaching that concealed environment required specialized hot water drilling systems, capable of melting a narrow shaft through ice thicker than many mountain peaks are tall. Although technical difficulties prevented the installation of certain long-term monitoring instruments, the expedition nevertheless succeeded in collecting valuable oceanographic measurements directly beneath the glacier. Those observations provide rare insight into water temperature, salinity, circulation, and conditions affecting the ice from below. Such measurements serve as critical benchmarks for improving numerical models and guiding future expeditions seeking to understand the glacier's evolving behavior. The public often focuses on one unavoidable question: exactly how much sea level rise is associated with Thwaites Glacier? The answer requires careful explanation because it involves several different timescales. Thwaites alone contains enough ice to contribute approximately 65 centimeters, or about 2 feet, to global average sea level if it were entirely lost over an extended period. Yet the glacier's significance extends beyond its own ice. Because it helps restrain portions of the broader West Antarctic ice sheet, continued retreat could eventually influence neighboring glaciers as well. Over centuries, widespread destabilization of that region holds the potential to contribute several meters, many feet, of additional sea level rise. Those figures understandably command attention, but they must never be interpreted as predictions for the immediate future. None of the major peer-reviewed studies published during 2026 concludes that global sea level will suddenly rise by meters within months or even a few years. Such dramatic scenarios remain unsupported by current evidence. Instead, researchers consistently describe an evolving process expected to unfold over decades, generations, and centuries. Ice discharge may accelerate following the weakening or breakup of the eastern ice shelf, yet the glacier's enormous mass ensures that its complete response requires long periods of time. The absence of an instantaneous collapse should not be mistaken for reassurance that the problem is insignificant. Slow-moving changes often become the most consequential, precisely because they continue long enough to reshape coastlines, infrastructure, ecosystems, and economies across multiple generations. For coastal planners, engineers, insurers, and governments, the distinction between immediate catastrophe and sustained long-term change is enormously important. Harbors, bridges, seawalls, ports, freshwater supplies, wetlands, transportation corridors, and densely populated coastal districts are designed with lifespans extending many decades into the future. Understanding how rapidly sea level may rise influences decisions worth billions of dollars and affecting millions of people. Scientific uncertainty also deserves careful attention. While confidence has increased regarding the glacier's overall direction of change, researchers continue refining estimates of precisely how quickly retreat may proceed under different climate scenarios. Newly discovered geological variations beneath the glacier illustrate why such refinement remains essential. A resistant bedrock ridge may temporarily slow retreat in one region, while neighboring soft sediments permit faster movement elsewhere. Small differences in ocean circulation can likewise alter melting rates beneath floating ice shelves. Rather than undermining the scientific consensus, these refinements strengthen it. Science advances by replacing simplified assumptions with direct observations. Every seismic survey, satellite measurement, ocean profile, and ice core contributes another piece to an increasingly detailed picture. The central message emerging from the latest research remains remarkably consistent despite these growing layers of complexity. Thwaites Glacier continues to lose ice, its grounding line continues to retreat, its floating eastern ice shelf continues to weaken, warm ocean water continues reaching vulnerable sections beneath the ice. Geological conditions hidden below the glacier influence the pace of retreat more strongly than previously recognized. Ancient evidence confirms that rapid inland retreat has occurred before once critical thresholds were crossed. None of these findings stand alone. Together they reinforce one another, creating a coherent understanding supported by independent observations collected using entirely different methods. Perhaps the greatest achievement of recent research lies not in predicting a precise calendar date for future change, but in replacing uncertainty with measurable evidence. Questions that once depended heavily upon theoretical assumptions can now be tested directly against observations gathered from satellites, seismic imaging, oceanographic instruments, autonomous underwater vehicles, and geological records preserved beneath the Southern Ocean. Every expedition narrows the range of possibilities while revealing the extraordinary complexity of one of Earth's most influential glaciers. Far above Antarctica, satellites will continue circling the planet countless times each year, silently measuring changes too subtle for the human eye to detect. Deep below the floating ice shelves, ocean currents will continue carrying heat through hidden passages carved over centuries. Across the glacier itself, fractures will lengthen, grounding lines will shift, and immense rivers of ice will continue their deliberate movement toward the sea. None of these processes unfolds with cinematic speed, yet together they represent one of the defining environmental transformations of the modern era.